So now let's change the focus and go towards another class of algorithms to solve the same optimization problem, and that is local optimization. So let's go classic. Let's say that I have a maximization problem and the landscape looks something like this. So instead of multi-population, I'll take only one individual. So that's my X. Now there's no need to use I. So all that I do at every point of time, I do a mutation. So a random noise. And then the parent and the child fight. So if f of y, it's a maximization problem, then I take y as my new individual, otherwise I just continue. So that's while stopping criterion, which is basically that I don't improve for a very long time. The swap doesn't happen for a very long time. And the algorithm is of course the hill climbing because it climbs the hill. So random mutation, accepted, 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 not accepted, so I'm still here, not accepted, so I'm still here, accepted, accepted, not accepted, so I'm still here, accepted, accepted, and from here, whatever I do, nothing will be accepted because I'm at the top. So that's hill climbing. It's a local optimization. Now the problem is if you start over from here, accepted, 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 not accepted, I'm still here, accepted, 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 and then whatever you do, I'll be here itself. So it gets trapped in local optima. There's a solution to it. It's called as the simulated annealing. So I say there's a probability P of accepting a worse solution and the probability is given by a basic principle that the probability of accepting a worse solution is directly proportional to the difference in fitness value. So if the two are almost competitive, it's just that the other one is marginally poor, then I've got a greater chance of accepting it, and I may actually accept it. But if the other one is extremely bad, then I might not actually accept it, and it's inversely proportional to time. So initially I'm more vulnerable, I'm more plastic, and that's where you get the name, which is annealing. So the metals are initially much easier to cast, and along with time casting them becomes difficult. They get into a non-plastic stage, and therefore I say probability of accepting a worse solution is e raised to power, so it will always be between 0 and 1. So I say it is f of x minus f of y divided by time, or actually a time function. So the only change that I do is all random number between 0 and 1 is less than probability of accepting a worse solution. So of course it's easy to write, and let's say that can I actually prove it? So again we start over from where was the problem. It was over here, so we actually start over from here. So accepted, accepted, accepted. So I go all the way up to top. Now there's a non-zero probability that I accept this, and this change. There's a non-zero probability. It can be extremely small, but it's non-zero. So there's a non-zero probability that I actually reach here. I'll have to accept this. There is a non-zero probability that I take these steps, and there is a non-zero probability that even though the new solutions are worse, I still accept them. So it can actually get rid of this small minima, and then I can, of course, all the way up over here. I accept it or not, I'll anyways reach it. Thereafter, there's a non-zero probability that I take this step and accept it, and then I take this step and accept it, and then I take this step and accept it. This time it's a longer optima, so I need to take probably 4 or 5 steps in the other direction. There's a non-zero probability that I accept these, and then I can go all the way up to over here. So theoretically speaking, there's always a non-zero probability of escaping the current optima. There's a non-zero probability of escaping the current optima and going into the other optima, and eventually, because there's a non-zero probability of escaping the current optima, you'll eventually end up into all the optimas, and eventually you'll end up at the global optima. And of course, ideally you return X in hill climbing. But then I could have always taken series of bad moves and returned that. So I say X best is X. So X is initially random. X best is X. And then of course I say that if f of X is better than f of X best, then X best is equal to X. So X best will only improve itself. It'll always be X. It's just that I could have taken a few bad moves right at the end, so I would have returned a non-best solution. So you make sure that on your part, whichever best solution you see, that is stored explicitly in X best, and that's the one that you return. Now, overall, what's more interesting is a local search versus a global, or as we call it, a multi-population search. So local search is always faster. There's only one individual, so the complexity becomes constant, and that virtually takes a few steps and converges. And this one is typically slow. So it's extremely fast. It's very fast. However, local search always converges to local optima, and with caveats, this generally converges to global optima. So that's good, and that is good. So you don't get everything. You get speed or you get optimality. And that's bad because now I have to choose between the two. There's a way by which you can combine a local search and a global search. And to get an algorithm that is fast and prone to converge at global optima. So let's look a few ways this could happen. So the first way this could happen is that you take in an initially random population and evolve them up as per the algorithm. So I take a random population and I evolve them in the algorithm. So they'll move as per some principles. And what I do is, at every few generations, I apply a local search to all the individuals. So all the individuals, they go closer towards the local optima. By genetic algorithm, it would have taken a long time, but I apply a few iterations of local search and all the algorithms make a few steps towards the local optima. So that's my strategy one. Apply a few iterations because it's very fast of local search to all individuals. After some time, repeatedly. So now the problem over here is that what's my complexity? So my complexity turns out to be a, let's say, normal genetic algorithm n log n, where n is the number of individuals, and this runs a total out for g generations. Now at every few generations, what I'm doing is additionally I'm doing a local search. So n times the number of iterations of local search that I do. This becomes my entire complexity. So I could make the algorithm more local by increasing L, reducing G, or I could make it more global by increasing G and reducing L, assuming total time is constant. So this is, G n log n plus NL is equal to constant, say. So I could make it more global by increasing G and reducing L so that the total becomes constant. So that's more global. Or I could make it more local by saying that I reduce G and I increase L. So if I make it more local, it will be faster, but then it can get converged into a local optima and vice versa. Now, a trick over here is that all these individuals were, in short, trying to estimate what is the total goodness of that modality. Is this the global optima? 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 And I was looking local use. Genetic algorithm would have made, you would have used a lot of iterations, so I did a local search to quickly find that out. And what I can do is that instead of applying it on all of them, I can actually apply it for a few of them only. Now it will be, instead of n, it will be on much few on C of them, where C is significantly lesser than n. The problem is, how do I select individuals? So here I say apply for a few iterations of local search to not all individuals, to some clustered individuals. Because if two individuals are very close, they are the same modality, I can apply it on any one of them. If they are far, then I need to apply to some clustered individuals. This unfortunately adds up to clustering time. So plus time for clustering. And clustering time, of course, could take up to n square complexity. But if your number of clusters are extremely small, it could take up to n log n complexity as well. Or it could take in a O of n complexity as well, depending upon the clustering algorithm used. So typically this could be extremely fast. But then clustering time is an overhead. So I first cluster them up and then I apply first some of them. So overall, that this is the Memetic framework, where you combine local and the global search. where the term memetic is derived from the term meme, very popular these days. In our context, meme is nothing but a trick, a local heuristic, which significantly improves the performance of the algorithm. So this local search was a trick that I injected in, and this strategy is what is the master slave strategy. So basically what happens is that initially itself, this individual goes extremely close to the actual optima, and this to go very close to the local optima. So you've got fair enough, in the first generation only, you've got fair enough idea of what the good individuals are. Then you apply the normal genetic algorithm that reproportionizes the individual distribution at different areas, get some convergence, some areas completely die off. Then you again apply this technique to get a better idea. Then again, you apply a few iterations of genetic algorithm, so some of the areas die off, some get a lot of extra individuals, some others, they are left with very few individuals, the population density is redistributed, then you again apply the slave algorithm. Now, this unfortunately can actually be still very large. If you want a very quick application of of local search, so the algorithm is say strategy 2. So what do? I of course generate random population. I apply a small local search to all individuals. And then I apply normal evolutionary search algorithm, which of course is global in nature. So that's again a extremely simple algorithm. So all I do is that my genetic algorithm is a global search. It's applied as default, no change in complexity, n log n times the number of generations. But what I do is I apply in a small local search only one time. So I think this should be a fraction of time that you apply. So some fraction of times of the total generation, that's constant out. And now you only apply it once. You only apply it at the first generation on all L of them. So you only apply it once for all items. If you want, you can cluster it up as well. So here the strategy is, instead of a master slave, the strategy is local produces the initial population for global, which is the same example. So out here we saw that in the first generation only, when all of them get nearer to the local optima, you get a fair enough idea which are good, which are bad. Then you don't need the local search. You can just apply normal genetic algorithm and get all the individuals convergent to the global optima. The chances that an individual was near its local optima and missing that out become reasonably small. The third strategy could be extended. Now, why apply it on all of them? Why not just one of them? And this again has a problem that the local search, some individuals which are, so you can have a global optima and no individual near it, and then all the individuals which were reasonably near it have also moved, so there is no individual near the global optima. So you want all the individuals to be evolved using GA alone. However, the last individual that you take that up and you apply some extra iterations to it. So that's strategy number 3. That's called as apply global evolutionary algorithm. And take best individual. and then apply local search. Let's see this one up graphically. So the complexity becomes interesting. So it's normal n log n for the genetic algorithm, and along with that you are just applying L iterations of local search on one individual one time. So I've got lots of these, and initially the population was random, and this was my global optima. Now, after some time, what actually will happen is I'm applying genetic algorithm, and the genetic algorithm will have all the individuals over here. Now, once you got into the correct optimality, now remember the genetic algorithm is a bad idea. Local search is a good idea because you have the global optima with you. So now why not just delete all the individuals? Why not just delete all the individuals, take the best one, and just use a local search? It gets you to the optima. Why maintain an entire population when you just need to converge? The local search is better. That's exactly what this is doing. It's waiting for all the individuals to get into the same modality. Remember that there's no, here in the diagram it was easy to see, but in the computer program all you see is fitness value numbers and the distance. It's impossible to find out whether, to guarantee that convergence has happened or not. What may appear to be beautifully converged may not have converged. You cannot see a high dimensional fitness landscape. It's impossible. The humans can only see 3D. We can only draw 3D here. So it's just a guesswork. So you somehow after some time make an intelligent guess that I've identified the correct global modality, I've identified the correct region, I've identified the correct modality. Here the modalities are only 3, they would be thousands. Then all you do is that you go deep inside it. Why maintain a population when local search will be better? So this is only local search, and this one is the global search. And once you do that, the global search is responsible for something much lighter. Now it only needs to get all the individuals in the same modality, and after some time you say I've identified the correct region where global optima is, then it's local search to carry out. So this is again the memetic framework where it's a unification of global and local search, and here we say that local search post processes, so something after the process, post processes the output of global search. So we in all looked at 3 strategy. The master slave one, where every individual looked around its neighborhood and tried to find out if it can improve itself by local search, and because it was getting too expensive, we clustered it out and we applied it on a few iteration only. But then I said that maybe applying it only on the first generation makes sense, then let the genetic algorithm take over. So it reduced computation time. The extra factor of the number of generation wasn't there. Local search could still take time. It's like multiple calls to an algorithm. So I applied it only one time and therefore I saved time. But then of course, once the local search finishes, then no individual can look at its neighborhood to find out if it can quickly improve itself with the help of local search. And then I said that strategy number 3, all I do is global search, let it converge as usual, let it come to the best region as usual. The local search was only post-processing it up. So once I say genetic algorithm globally has done a good enough job, I've got an individual which is reasonably at a good place, then the quick convergence of it inside the current modality was purely and purely the job of a local search only.